In 2017, a massive petrochemical plant unexpectedly tripped offline. Operations halted, and engineers initially brushed it off as a routine mechanical glitch. But investigators examining the network found something hiding in the system's memory, a piece of custom malware known as TRITON. The malware was actively rewriting the in-memory firmware that controls the physical machinery. This discovery absolutely terrified cybersecurity experts. The attackers didn't steal data or demand a ransom. They engineered a digital weapon specifically to disable safety mechanisms, aiming to cause catastrophic physical damage and loss of life. The attackers completely bypassed the facility's corporate information technology network and the standard operational technology networks that run the day-to-day manufacturing. Instead, the malware hunted down a highly specific, obscure piece of hardware, a Schneider Triconex controller. That device is what engineers call a Safety Programmable Logic Controller, or Safety PLC. It is the single, isolated layer of defense standing between a normally functioning plant and a total disaster. To comprehend the lethal intent behind this cyber weapon, we must look at the specialized engineering of the hardware it was trying to kill. An industrial plant's architecture is split into two systems. The process control network acts as the brain, continuously running machines. Completely independently, the safety instrumented system acts as an involuntary reflex, triggering an emergency shutdown if critical thresholds are breached. A standard PLC keeps a factory making money. A safety PLC keeps it from exploding. Safety PLCs rely on redundant hardware, using dual parallel processors that constantly compare identical data streams. They also employ voting logic. If 3 sensors monitor a valve, the system acts only if 2 report a dangerous spike, preventing unnecessary shutdowns. Even at the software level, this separation is rigid. In modern systems, the safety code is isolated into distinct bright yellow programming blocks, ensuring developers never confuse a critical safety function with an everyday operational command. These redundant, highly structured architectures are engineered to mathematically guarantee that if any single component breaks, the entire system defaults to a safe state. But there is a glaring vulnerability at the core of all this engineering. Historically, industrial control environments were physically isolated from the outside world, meaning they operated on a model of implicit trust. Because of that legacy, modern PLCs lack internal mechanisms to detect if their code has been maliciously altered. They are defenseless by design. If an attacker breaches the controller, the machine faithfully executes those malicious instructions with the exact same ruthless efficiency it normally applies to saving lives. Over the last decade, the drive for data visibility and predictive maintenance created a convergence trap. Operators began linking their once isolated safety PLCs directly to broad, internet-connected plant networks. The attackers behind TRITON exploited this exact convergence. Moving laterally from IT networks into operational technology, they aggressively overtook the plant's Triconex safety controllers. But the facility was saved by an ironic twist. A bug in the malware's code caused the safety PLC to register an internal logic anomaly. The plant survived because the safety PLC did exactly what it was mathematically engineered to do. It detected a fault, failed safely, and shut the physical plant down, exposing the hackers. In response to TRITON, engineers are developing new digital defenses, like scan-time code monitoring, which analyzes the time a PLC spends executing a routine to spot suspicious internal behaviors. Yet, the final, unbreakable layer of security requires physical, hardware-based mechanical overrides. Devices like spring-loaded pressure relief valves and mechanical burst disks operate entirely upon the strict laws of physics. Regardless of a hacked sensor's report, when physical pressure gets too high, the mechanical valve opens. They are completely immune to network compromise or digital manipulation. As cyber weapons grow increasingly sophisticated in their targeting of digital infrastructure, the ultimate failsafe for human life will always rely on the unhackable reality of analog physics.